Hi there. So this is a little bit of review from geometry. So we're going to look at three different types of problems, which kind of build on each other. So the first type of problem that we have in this section is we are solving for a missing side of a right triangle. These are all right triangles that we're working with. So you're solving for a missing side. In the next section of examples, you're solving for an unknown angle. And then in the last section of examples, you're solving a triangle, a right triangle completely. So you're solving for any unknown angles or any unknown sides. Okay, so for this first section of examples, if we look at example 1, we're thinking SOHCAHTOA. Right, that sine is equal to the ratio of the opposite side over the hypotenuse, cosine is equal to adjacent over hypotenuse, and tangent is equal to opposite over adjacent. So looking at this first triangle, we're given that angle A is equal to 43 degrees. We do not know what the length of the side opposite to 43 degrees is, but that's what we're trying to find. And then we're also given that the hypotenuse is a length of 13. So with the given information, using that angle of 43 degrees, since we're solving for the side opposite that angle, that means we're either going to be using sine or tangent, right? Because those are the trig ratios that involve an opposite side, the side opposite of a given angle. And then because we are given the hypotenuse, that means that we're going to want to use sine to help us solve for side x. So sine of 43 degrees is equal to opposite, which is x, over the hypotenuse, which is 13. So then we can just use a property of equality, multiply both sides of the equation by 13. So we get x is equal to 13 times sine of 43 degrees. 43 degrees is not an angle that's on the unit circle, so we cannot evaluate it exactly. We're going to need to use our calculator. So this is the side x written as an exact value, but we want to give ourselves a decimal approximation. And I know that the directions here say to round to the nearest tenth. However, to stay consistent with the AP exam that you guys will most likely be taking next year, I'm going to say you guys need to round to 4 decimal places, so to the 10,000th place. So make sure that because we are in degrees, so you're evaluating sine in degrees, make sure to hit your mode button and check that in row 4, degrees is highlighted, right? So if we were in radians, we would want to make sure radians is highlighted. Okay, but once you make sure that your mode is in degrees, then you can just type in 13 times the sine of 43. And I get 8.8660 for rounding. Okay, so x is approximately 8.8660. Okay, let's do one more here. So looking at the information that we're given, we know that angle B is 24 degrees. We are solving for the side opposite, x. So again, we're either going to be using sine or tangent, that tells us. And then we are given the side adjacent to the angle 24 degrees. So that means we're going to want to use tangent, right? So tan of 24 degrees is equal to opposite over adjacent. Okay, so again, we can now apply our property of equality, multiplication property of equality, and multiply by 11.4 on each side of the equation. Okay, pop that into your calculator, and we get x is approximately accidentally typed in 1.4. So I get x is approximately 5.0756. Okay. And let's maybe look at one more. How about let's look at number 4. Okay, so we are solving for the side that is adjacent to the given angle of 28 degrees, and we are given the hypotenuse. So that tells me that I'm going to want to use cosine. So cosine of 28 degrees is equal to adjacent over hypotenuse. Okay, so again, multiplying by 2 on each side of the equation, we'll have 2 times the cosine of 28 degrees is equal to x. So x is approximately 1.7659. Okay, and let's just do number 3, just for good measure. Okay, so we are solving for the hypotenuse. In this case, x is the length of the hypotenuse, and we are given the side opposite 24 degrees. So opposite over hypotenuse, that tells me I want to use sine. So sine of 24 degrees will be equal to 7.6 over x. Now this is a little bit different than the other 3 examples because x is in the denominator of the ratio. So we're going to need to multiply by x on each side of the equation so that we would have x times sine of 24 degrees is equal to 7.6. And then we can divide by sine of 24 degrees on each side. So x is equal to 7.6 over sine of 24 degrees. It's a 4. And then after popping that into my calculator, I get x is approximately 18.6853. Okay, so for the next set of problems, we are solving for an angle. So looking at this triangle, we're solving for the angle theta. Now, we're going to have to use something new on our calculator. So let me get some blank space over here. So let's think about if we had, I don't know, how about sine of theta is equal to root 2 over 2. Now, because root 2 over 2 is a ratio on the unit circle, you know that theta is equal to 45 degrees, or theta could be equal to 135 degrees, or any coterminal angles to those angles. But let's say that we had sine of theta equal, let's say root 2 over 2 is, we didn't know or recognize that that's a ratio on the unit circle, and we wanted to solve for an angle theta that would make this a true statement. So what we could do is to take the inverse sine of each side of the equation. Remember when we studied inverse functions with the beginning of the year, and I drew this picture of, like, let's say if this is the function f, and this is the function f inverse, or function machines. And we had 2 as an input into the function f, and it spit out 4. And we could take 4, and when we input it into f inverse, we will get 2 as the output, right? Their domain and ranges are opposites of each other. They switch. So when we take the inverse sine of each side of the equation here, we would get that theta is equal to inverse sine, right? This notation should look familiar from the notation for an inverse function, right? That's not sine being raised to the negative first power, although this notation can be a little bit confusing. But it's the notation that you should see on your calculator as well. If you hit second and then sine, you see right above the sine button, it has the sine inverse in this notation. So for the inverse trig functions, ratios are now going to be the inputs and angles will be the outputs, right? Because in this original trig function, we could think of angles, so for sine of theta, angles are the inputs and the outputs are ratios of y over r, right? And then for inverse sine or any of the inverse trig functions, ratios will be the inputs and angles will be the outputs. So now making sure that our calculator is in degrees because we want to know the angle in degrees, you could type in second sine, right, to call up sine inverse, and then type in root 2 over 2, and you would get theta is equal to 45 degrees. Okay, but notice that you only get one angle. Well, it's because inverse sine is a function, right? And every function, for every input corresponds to exactly one output. We're going to study the inverse trig functions more in second semester, so we'll really look at why that is, why we're only getting one angle whenever we evaluate an inverse trig function at a ratio, right? Because we also know that 135 degrees, it makes that a true statement, right? Sine of 135 degrees is equal to root 2 over 2. Now, for what we're using the inverse sine functions, the inverse trig functions for solving, helping us to solve triangles, next class we're going to be looking at solving oblique triangles as well, is that the ratios that we're going to be using, at least for right triangles, are all going to be positive, right? Because the sides represent lengths of the sides of triangles. They're going to be positive values, so our ratios are always going to be positive. Therefore, when we use the inverse trig functions, we're always going to get an angle from quadrant 1 for our right triangles when we're solving for an angle in one of our right triangles. Okay, so you guys should also be familiar with some of the other notation for inverse trig functions. So like inverse sine of x is equivalent to arc sine of x, or inverse cosine is equal to arc cosine of x, and inverse tangent of x is equal to arctan of x. Okay, so looking over here at this first example of solving for an angle, we are finding the angle theta, and we're given the side opposite the angle and also the side that is adjacent to the angle. So that tells me that tan of theta is equal to 4 over 9.6, right? Opposite over adjacent. And that is not a ratio that lies on the unit circle, so we need to use inverse tan. So theta is equal to inverse tan of 4 over 9.6. So to type that into the calculator, I hit second tan and then type in 4 over 9.6, close parentheses, and I get theta is approximately 22.6199 degrees. Okay, let's do another one. Erase this. Okay, so we're solving for theta, and we are given the side opposite to theta as well as the hypotenuse. So opposite and hypotenuse, that tells me I'm using sine. Sine of theta is equal to opposite over hypotenuse, 5 over 9. Again, not a ratio that's on the unit circle, so we are going to use inverse sine to determine what theta is. So again, hitting second and now sine to call up inverse sine on my calculator of 5/9 is approximately 33.7490 degrees. And our calculators might have slightly different answers, and that's okay. I take that into account when I'm grading. Okay, so why don't we look now down at just solving triangles. So I'm moving down here to number 9, and we can see that we are missing the side opposite to angle A, so I'm going to call that lowercase a. And we are missing angles A and angles B. So I can determine what A is using Pythagorean theorem, right? Because this is a right triangle. So A squared plus 10 squared equals to 13 squared. So A squared is equal to 13 squared minus 10 squared, which is 69. So A is equal to the square root of 69. That's the exact value. I could pop it into my calculator for approximation, but I'm just going to leave it as the square root of 69. Okay, so now that we have all three sides, we can use our trig functions to solve for our angles. Let's just go in alphabetical order for now. And I want to use the given information as much as possible. I know the square root of 69 is an exact value, which is great, but I want to use exact values or the given values as much as possible, and you guys will see this when we are using law of sines or law of cosines to solve oblique triangles. So looking at what I'm given, the side adjacent to A and the hypotenuse, cosine of angle A is equal to 10 over 13. So A will be equal to the inverse cosine of 10 over 13. Angle A is approximately 39.7151 degrees. Now we can use the fact that the angle should sum to 180 degrees to solve for angle B, or we can keep using trig functions. I'm going to keep using trig functions. So I'm going to use sine of B. You have options here. There's not one right way to do this. So sine of B is equal to opposite over hypotenuse. So B is equal to the inverse sine of 10/13. So inverse sine of 10/13 is 50.2849 degrees approximately. Okay, so we have the missing side and each of the missing angles. Okay, this video is getting pretty long, so I'm going to end it there, but basically you can use the trig functions or you can use Pythagorean theorem when possible to try and solve for the missing sides and missing angles of a triangle.